Is it recording?
Yeah.
Okay. So I guess we'll get started. Hey everyone, my name is Kieran. I'm doing the Solana Workshop today. I'm one of the university ambassadors for the Solana Foundation, Solana University. For a bit more background on myself, I'm a student currently at Rutgers University. I have a blending club over there, and I've been doing Solana dev since about early last summer. So before we start, these are just two resources you can use. There's the Solana University Notion page for Lionhack, which has a bunch of information about prizes and a lot of different resources that you can use to get some guidance on development. And then the Solana University Discord, they hold like office hours. You can get in contact with the developer relations engineers if you need help on any specific problems and things like that. Is this?
Test it out, yeah.
Test. So yeah, on these two links, you'll be able to find a ton of resources just about Solana development in general, and to get some additional help if you run into any problems if you do choose to develop on Solana. So here's a look at the agenda that we'll go over the next about like 25 minutes to a half hour or so. I'll be providing a pretty high-level overview of Solana's architecture and how it's different from other chains, as well as a look at the general Solana programming model. This will include things like how data and programs are handled on-chain, and then finally we'll be moving into a short walkthrough on some of the different aspects of the Solana Programming Library, or SPL for short, as it's commonly known. This workshop definitely won't be the end-all be-all for helping you build your project this weekend, but I hope it serves as a good introduction to what sets Solana apart from some of the different chains and highlights some of the competitive advantages or things you can do on Solana that you can't on other networks. So first we're going to start off with some of the technical advantages of Solana and what sets it apart from other layer ones. So the first of these is obviously the fast confirmation time. So on Solana, we're not just talking about like the time it takes for your transaction to get included in the block, but also the time it takes for your transaction to achieve finality. So on Solana, I believe it's about 400 milliseconds to achieve ultimate finality. For context, it takes about 15 seconds for your transaction to get included in the block on Ethereum and about 10 minutes to achieve ultimate finalization. So it doesn't happen too often, but your transactions can get reversed on Ethereum shortly after you send them. This is not possible on Solana as it executes so quickly in about four-tenths of a second. So the second is obviously low transaction fees. Fees on Solana typically come out to somewhere around like an 80th of a cent. Obviously, that's much cheaper than Ethereum. Even with layer 2s, they still come out to, you know, I think currently it's 20 cents, but best case scenario, it gets down to 1 cent. That's still an order of magnitude larger than what can be currently provided on Solana. So obviously, this is all while maintaining a pretty robust consensus across a network of over 2,500 decentralized validators, all in parallel. And these competitive advantages offer themselves quite well to specific UX improvements. Users don't have to wait more than a second to know whether their transactions have gone through or not, and they pay a negligibly low amount to get their transactions included in blocks. It's obviously up to you guys to use these advantages as you guys see fit in your project, but it lends itself quite well to faster trading experiences. You can build things like central limit order books on Solana that you can't on something like Ethereum, as well as consumer apps or gaming apps where you need fast finalization, as well as things like micropayments and a ton of other stuff where speed is of the utmost priority. So we're going to take a pretty broad overview of how the network is constructed, how consensus is achieved, and how transactions activated simultaneously pretty much. If you work with things like parallel processing or something like multiprocessing or multi-threading, maybe in some of your CS classes or other projects, this will seem pretty familiar because it essentially operates in the same way. So with these kind of three aspects that I mentioned all in combination, it serves in the common purpose of creating a super fast throughput chain that's able to execute transactions in parallel at a very cheap cost. This can lend itself to some pretty interesting projects. One of my favorite examples that I like to cite a lot is on a sequential execution chain like Ethereum. You actually can't create true delta neutral like products or options or things like that to hedge your positions. Because there will always be some tiny amount of delta in between the different transaction executions. On Solana, you can execute two things at the same time, like buying two positions that hedge each other out, so you can achieve true delta neutrality, which you can on some other networks. So the most popular innovation that people cite about Solana is proof of history. It basically leverages what's called a verifiable delay function to allow all nodes in the network to agree on the passage of time. This is a pretty unique way, and it was actually a pretty hard problem for a long time to solve in decentralized networks. It's basically creating a decentralized clock. So getting a bit deeper into it, it's you can essentially imagine that you have some bit of information that you're going to hash, and you always know exactly how long that hash function is going to take. So if you run that hash function multiple times, you can know how many of those function calls have passed. And I won't get too deep, but it's essentially a way for multiple validators in the network to achieve consensus and agree on a certain piece of information just by knowing how much time has passed, because they're able to trace it back based on a certain indexing of the hashes and see how many of those functions have occurred. So some of the takeaways from this first section are just generally Solana has extremely fast confirmation time. It has no transaction fees, low transaction fees, no mempool, it executes in parallel, and it's ideal for high performance applications. Like I mentioned before, the most common example is often central limit order rows. So I put this on screen before, but this is kind of the general agenda that we'll be taking. I'll now get into Solana's programming model, and then shortly after that into the SPL token standard and how that relates to minting different tokens and minting NFTs. So right now we'll get a bit more into the programming model. So we're going to start with a concept called accounts. On Solana, everything is an account. We'll flesh out this idea a little bit more, but for now, you can kind of just think of everything as a functional account. So here are some basic rules about an account. You can see them on the right there. It holds some balance of SOL. It has a unique 256-bit address. It stores some amount of arbitrary data, and data storage is paid with rent. Rent at a high level is essentially it can be distilled down to paying a fee for the validator based on how much space or how much memory you take up on the validator's hardware. This isn't usually something to worry about too much. It's basically just to discourage users from storing a large amount of data on the validator's hardware for no reason, like when you don't really need to. So it's just kind of to discourage that bad behavior. So a few more rules. Anyone can credit SOL or read data from an account. But only the account's owner is allowed to debit SOL or actual accounts look like in their raw form. You can see it here. So I can't see it too well from my angle, but you basically have a key that designates the number of the account as well as LAN ports. LAN ports are essentially just a smaller unit of SOL. And then a uint array to store data inside the account, as well as an is executable Boolean. This basically tells you, is this data a program? Right now, you can kind of think of programs as functionally equivalent to smart contracts on other networks, but as we get deeper into the presentation, we'll get a bit more into the differences between them. And then as long as the owner, the person that has right access to the program. So, like I mentioned before, programs can kind of functionally be thought of as equivalent to smart contracts from a chain like Ethereum or Avalanche or some of the other sponsors. This is a good way to think about it at a high level, but in practice, there are a lot of subtle nuances and differences between a smart contract model and how Solana programs actually operate. So as we kind of get through more of this, you'll see kind of what those differences are. So there's a special type of an account that is an executable program, like we mentioned before, with that Boolean for every account data. Right now, Solana programs can be written in Rust, C, C++, or Python, and I believe they're planning to expand into more languages like TypeScript and Golang, and hopefully more in the future. So, right there. So data on Solana is organized as eBPF bytecode. You don't have to get too deep into this. This is kind of like if you're more familiar with the design of Linux, this might be familiar to you. BPF is the Berkeley packet filter, and Linux uses this to handle their data and kind of as an interface to work with some stuff within the operating system. You guys are familiar with how some of that stuff works. Solana's can kind of be thought of as a distributed Linux kernel. That's not a great parallel, but it does suffice for some things. So one thing about programs is that they actually are stateless. They don't have a state or some type of data that it needs to store like a smart contract on Ethereum. They perform reads and writes all from accounts stored on the chain. To perform a write, the program must be the designated owner of the account that it's attempting to modify, and anyone can perform a read, obviously, as it's permissionless, it's a public blockchain. So programs are designed to process what are called instructions, and they can also send these instructions to other programs on the network. Going back to that stateless feature, this is really what differs it from the traditional smart contract model. As I mentioned before, all data on Solana, and it's really totally inclusive, all data is stored as accounts. So it's a bit of a weird roundabout way to think about it, but every single program that you're interacting with on Solana, its data is all external and stored on other accounts on the network. This is also essentially what allows for Solana's parallel execution environment. So some takeaways from this section: everything is an account. All accounts hold SOL or land ports on a smaller unit. Accounts can store any amount of arbitrary data, and they can also store executable programs. And then accounts are passed into programs, allowing for parallel execution. Data is always stored externally from the program in accounts. So now we'll get a bit more into instructions. We mentioned before that programs are designed to process instructions. They're essentially the mechanisms for actually invoking, essentially allowed to interact with it and execute it in some cases. So now we'll get into the transactions. Transactions are actually the vehicle that you use to send instructions, which we talked about just now, to the Solana network. Every call, every time you call a function, every time you interact with a different program, these are all executed on-chain as transactions. We essentially package up a bunch of data. You guys are probably familiar with this if you're just generally aware of how blockchain architecture works. It's the same way on Solana. You essentially package your data up into what we call a transaction and then pass it along to the RPC client. This will then forward it to the broader validator network on your behalf, which obviously then gets included in the block. So this is the schema for what a raw transaction looks like. It contains the message, the list of instructions, the recent block hash, which is essentially to maintain the fact that they are non-duplicate transactions, so you can't have the same one being confused by multiple validators in the network. Every single transaction will always have a unique block hash. And then the signers array at the bottom. So the signers array is pretty interesting. It's essentially an array of buffers, and each of these buffers is basically the entire transaction encrypted with the signer's private key. So if you guys are familiar with some of the fundamentals of cryptography, this will definitely seem familiar, as you're able to decrypt these buffers within this array using the signer's public key. So you can essentially always verify that a certain transaction has been carried out by a certain wallet by simply decrypting it with their public key. So some of the takeaways of this section: programs are invoked by instructions. Instructions are sent via transactions. Transactions are atomic, and they must always be signed by an account. So we're going to move on to a bit more complicated stuff and touch on why some of Solana's design decisions can actually serve for some powerful use cases. We're going to get a bit into custom program data and things like account derivatives, and then also later on into the SPL token library. So like I mentioned before, what about storing custom program data? App or interface or something like that is reading and writing from a database whenever it pleases. It's freely interacting with it. So in a Web3 world, it takes on a bit of a uniquely different form. We have to make use of the account ownership rule operates. The most common way to set this up is a collection of accounts owned by a program using a Solana feature called the program-derived addresses. So this is pretty much exactly what it sounds like. It's an account whose address is derived from specific input-output method for deriving addresses. Can be extremely useful for relating data and kind of indexing it together. Like I mentioned before, kind of using the analogy of a SQL database. So So one of the other features of program-derived addresses is the ability for programs to create signatures to auth. The account's private key is obviously used to sign the transaction and then authorize a change to the state. So we want to look at now how PDAs operate program-derived addresses with example of a table of user profile information. You can see here we're recording each user's address, their username, and then some arbitrary information about them. Here we have email. So the problem that we're trying to solve is how we can represent this table or database as whatever, the address, and now additionally their profile address, which we saw can previously derive only from their wallet. You can see how deriving these seed patterns can help us relate across the different types of accounts on Solana. This technology, PDAs, can be used to relate data across accounts, and PDAs don't have private keys. The program can sign for them. So these are pretty useful, like I said, for managing data in a ton of different ways. This DApp, and the DApp will then send their transaction to an RPC client. This RPC client will then route that transaction to a validator within the validator network, who will then process it, include it in a block, and make sure that transaction is finalized, state of an exterior account. All data is always stored as an account, never in the program. And then, of course, it updates it to 1 as it should with the increment function because it's still at 0. So this is a pretty high-level overview, but it's very important to just understand how transactions actually occur in the network, how state is managed, how things are included in blocks and things like that. So some takeaways from the section. Applications send transactions to an RPC client like they do on most other networks. The RPC client forwards transactions to the network. The validator executes these transactions, carries out the instructions derived in the program, or rather their transactions invoke the programs, which invoke the function calls, and then programs update the account state. Once again, state and all data is always stored as accounts, not as programs. So now that we've covered some of the fundamental programming concepts that are native to Solana, we'll talk a bit about tokens and how they operate, as well as NFTs. So similar to Ethereum with its ERC20, Solana has a token standard on its network. This is called the SPL token standard, but they actually operate quite differently to how they do on Ethereum. The biggest difference is that Solana actually uses native programs deployed natively to the chain to manage the creations of new tokens. Essentially, a way to think about this is if there was some global ERC20 smart contract that was always deployed on chain, and you could just call things like mint functions or transfer functions and stuff like that, instead of having to deploy your own function if you want to create a token. So a token on Solana is represented by an account called a mint, and this account has the core information about the SPL token mint, as well as things like the balance and stuff like that, showing that it actually exists in someone's account. So as you can see here, there are a handful of other accounts that relate to the mint account, which facilitate certain actions or properties of that token. To track a wallet's balance of any mint, we use an account called an associated token account, which, as you can see, relates both the mint and the wallet. We'll get into this a little bit more later. So for any associated metadata for a mint, such as images, titles, things like that you might want to store with a token, either as a name or a ticker, or maybe with an NFT in the form of an attached image or an attached program, we leverage one or more metadata accounts as it's shown up there. These are created by the metadata program, but this is actually not a Solana native program like some of the token libraries are, but it does play a role in the broader metadata standard. We'll get into this a bit more later as well. So the kind of dashed lines between these programs, these seed lines as you can think of them, are actually what we talked about before with the PDA standard, the program-derived addresses. So the key here is that, unlike other chains like Ethereum, you don't actually need to deploy any programs or smart contracts on-chain to create a token. Like I said before, on Ethereum, you need to deploy your own ERC20 contract if you want to mint the token. On Solana, you can do this entirely with RPC requests, with transactions that you execute externally. So as long as you put these 4 transactions in order and send them to the network in some way, you can create a token without writing any Rust or C or C++ or what have you, and without deploying any smart contracts. So you can do this in JavaScript or Python or any language you like, as long as you can make RPC calls to an RPC provider. So this is pretty unique compared to some other chains. So some takeaways, you don't have to deploy a program to create a new token. You can create tokens using only RPC calls, like I said. You can do it entirely off-chain. And related accounts are also used to describe tokens. That was kind of the dashed line between the diagrams that I was talking about before. So now we're going to tie it all together and kind of show practically how tokens work on Solana. This will be a walkthrough process of creating an NFT and minting it to a user's wallet. So you're going to create a new account for the mint. This is the first step. And then you want to initialize that account as a mint by adding the required data that we previously saw on some other slides. We want to create any desired metadata accounts as well. You can modify these in a number of ways, but the most simplest that you'll often see is like an image associated with an NFT or a title associated with a token. At this stage, we've essentially functionally created a token. This is all you need to do, but it won't exist in practicality because the balance will be zero for any wallet that holds that token. So if we want to actually have a transferable token that exists on the network, we'll move to the next step. We need a wallet to mint the token to. So you create an associated token account for the user's wallet, where you can then store the balance of this new mint inside of the wallet. And finally, you can use that token program to mint a new token to this user's associated token account. All of these steps are done, once again, by sending instructions for each of these respective programs that are already a part of the Solana native token standard. So this nice man here, Joe, who very graciously created the slideshow for us, will be going through some of the examples of how to create a custom Joe NFT. So like I said before, you create the new account for the mint. You then move into the initialization of the account as a mint. And then you give our token an icon by creating a set of associated metadata. So in this, it's that picture of Joe's beautiful face. Once again, at this stage, we've, sorry, some of my slides got messed up. So sorry about that, I cut out a bit there, but this is very similar to the diagram in the past, where instead of just having some like desired metadata, we have Joe's beautiful face there, and then instead of just having one wallet, we have a connection of wallets. So Joe's collection of friends that he wants to airdrop his beautiful face to, you'll be able to send that NFT to all of their different accounts, essentially airdropping it to them. So takeaways from the section: a mint must be created and initialized before it can be minted to someone. An associated token account is required to get the token into someone's wallet. And there's a new token standard, semi-new, Token 2022, that introduces new features for different SPL tokens. So we'll kind of get more specific into NFTs right now. Sorry, just one second. Obviously, I mentioned metadata a lot. The most prominent use of metadata is, of course, with NFTs in different forms. And a lot of these are pretty unique on Solana specifically. But we'll talk about kind of the base properties of an NFT right now. NFTs on Solana always have 0 decimal places, and the ability to mint a new token is disabled after 1. So you're going to have a unique token type for every single NFT that you mint, and NFTs cannot be fully fractionalized in a native way. Fractionalized NFTs do exist on Solana, but they kind of use interesting workarounds. In the most basic SPL implementation that you guys will probably use when we're going over here, they cannot be fractionalized. So some of the interesting things that you can do on Solana that you can't necessarily do on other chains are things like a master edition, where the NFT will serve as a single unique master copy, while allowing for print versions to be created based on it. You got to think of this as like maybe a digital comic book where there's an edition number 1 and then there's existing prints created after that. could also belong to a collection which has its own metadata. This is of course very popular with NFTs as kind of a greater set of something like 10,000 all serving as part of one single collection. There also are things like programmable NFTs, which have been gaining a lot of traction lately and are pretty interesting if any of you guys want to look more into that to do the project. And then of course things like royalties, which have caused a lot of controversy in the past couple months, but are possible with things like programmable NFTs and some of the unique metadata that you can associate with the NFT accounts. So some of the takeaways, like I mentioned, NFTs have 0 decimal places and the supply of 1. There can only be a single SPL token associated with each NFT, and they cannot be natively fractionalized. You can do it in some weird ways though. And then the NFT metadata is highly customizable, especially a lot more so than some other chains. You cannot do things like programmable NFTs, or you can store a large amount of data on chain, things like Ethereum or even Layer 2s. So yeah, I want to thank you guys. This was a pretty high level overview. I know I kind of dashed through a lot of different things, and just kind of gave a broad overview of the different parts of Solana's architecture and how some things like the SPL token standard operate and things like that. If you have any more questions about some of the specific aspects, you can definitely reach out to me or reach out to someone on Discord. I showed these links before, but I'll show them again. We have the Solana University Notion showing information about the prizes that Solana is offering for this hackathon, as well as a bunch of different resources that you can look at for maybe some help with guiding the development of your projects. And also we have the Solana University Discord, come join the community. And also if you need help to solve some problems that you might encounter during your projects or get over some humps, there are a number of super friendly developer relations engineers there who can definitely help you out with any problems that you might run into. So yeah, thank you everyone.
That's awesome, Karen. Can I say one thing that also on the website for solanau.org, there's a fully functional GPT-4 chatbot that you can actually ask how to make an account, and it will show you how to do it. So play with it.
Yeah, I believe that, as well as like a ton of other things like GitHub repos and even the slides from this workshop are all linked on the Notion as well. So.
Yeah, maybe if you could sell or share the slides in Discord.
Yeah, they're on the GitHub, like one of the workshop's GitHub repos, so I'll post the exact link, but they're all there. Cool.
I'm sure people would love to see that.
So, yeah, thank you guys. I'd be happy to answer any questions. If there's a ton of people online who can share some more information. So, congratulations.